All right, 6.2 is about the binomial distribution. In 6.1, we talked about discrete random variables in general, discrete probability distributions. And in this section, we'll talk more specifically about the binomial random variable, the binomial distribution. So in order to use the techniques in this section, you first have to determine whether or not the scenario you're confronted with is in fact a binomial scenario, okay? So to help you determine that, here's what we mean by binomial, okay? So an experiment is said to be a binomial experiment if it satisfies these four conditions. So first of all, the experiment has to be performed a fixed number of times. Each repetition is called a trial. Number two, the trials have to be independent, right? So the outcome of one trial does not affect the outcome of another trial. Number three, for each trial, there are two mutually exclusive, or another word for mutually exclusive is disjoint, right? So two mutually exclusive outcomes, success or failure. And see, those words from chapter 5 are coming back to haunt us, right? Independence, disjointedness, right? Anyway, and then number four, the probability of success has to be the same for each trial of the experiment. So those are the four conditions that have to be met in order for an experiment to be binomial. Now, if you count up the number of successes and you call that x, then x is called a binomial random variable, okay? So the number of successes x and n trials of a binomial experiment is a binomial random variable. So for example, tossing a coin 3 times is a binomial experiment, right? You're performing the experiment a fixed number of times, right? 3 trials, 3 tosses. Each trial is independent, right? Your first flip has nothing to do with your second flip, right? For each trial, there are two mutually exclusive outcomes, heads or tails in this case, right? And the probability of success is the same each time you flip the coin. So yeah, binomial experiment for sure. When you're doing binomial experiments, we're going to use this notation, okay? So a lowercase p is going to stand for the probability of success. And the probability of success is the same in each trial of the experiment, so you don't have to have different probabilities, right? They're all the same, right? So p is the probability of success in each trial. Q is the probability of failure. So by the complement rule, Q is just 1 minus P, right? If you don't succeed, then you fail, right? So Q is 1 minus P, complement rule. Little n is the number of trials, as usual. Capital X is the number of successes in n trials. Note that the values x can take on are anything between 0 and n. It's possible you have 0 successes, but it's possible that all n trials end up in success. And then anything in between could also happen, right? So x could be anything between 0 and n. P of x is the probability that x equals x, right? That capital X equals lowercase x. In other words, it's the probability of obtaining exactly x successes among the n trials. So what I want to do is take you through several examples. We'll determine if the example we're looking at is binomial, and if it is, then we'll identify what constitutes success, the number of trials, the probability of success, the probability of failure, and the possible values for x. Okay. So part A says a player rolls a pair of fair dice 10 times and the number of 7s is recorded. Okay, this one is binomial for sure. It's binomial. Okay, when they say the number of 7s, what they mean is like obviously a die, a typical like 6-sided die only has 1 through 6 on it. But when they say 7, they're talking about you roll the 2 dice and then you add up the numbers. And if the number is a 7, then that's considered success, right? So if the sum is 7, then that's success. Excuse me. If the number is 7, you get success. If the number is anything else, right? If the sum is 8 or 4 or whatever, then that's considered failure. So this is binomial. Okay, you're performing the experiment a fixed number of times, 10 times. The trials are independent, right? Rolling the die, like your second roll is not dependent on your first roll at all. For each trial, there are two mutually exclusive outcomes. Probability of success is always the same. So yeah, binomial. Success here is rolling a 7. So success is rolling a 7. It wants the number of trials. Number of trials we said was 10, right? Because you're going to roll the pair of fair dice 10 times. So n is 10. Probability of success. Ooh, well, let's pull up chapter 5. I think we listed out all the possibilities in 5.1. So I'm going to pull out my 5.1 notes. Yeah. In 5.1, so this is section 5.1, page 2, where we listed out all of the possibilities, right? These are all of the possible outcomes when you roll a pair of fair dice twice, okay? And we are looking for the probability of success. In other words, we're looking for the probability that we roll a 7. Well, we computed that in part C, right? We said it was 6 out of 36, right? All of these are 7s on this main diagonal. So it's 1, 2, 3, 4, 5, 6 out of 36 possibilities. Okay. So 6 out of 36, or in other words, 1/6 when you reduce it. So there's the probability of success. That means the probability of failure is 5/6, right? If there's a 1 in 6 chance that you succeed, then that means there's a 5 in 6 chance you fail, right? Okay. And then the possible values of the random variable x, well, it's possible you could succeed 0 times out of your n trials. It's also possible you could succeed once or twice. Or it's possible you could succeed all 10 times. It's probably not very likely, but it could happen. You could just so happen to roll 7 or 10 7s in a row, right? Could happen. Okay, so there's that one. Part B says 3 cards are drawn from a deck without replacement and the number of aces is recorded. Okay, so this one is not binomial. It's not binomial. It's almost binomial, but it's not quite binomial. Here's why it's not binomial. Condition 2 is not satisfied, right? The trials are not independent because you're drawing the cards without replacement. In other words, once you pick one card, you're not putting it back in the deck before you pick the next one. And that means the probabilities are going to change, right? Like the probability you draw an ace on your first draw is 4 out of 52 because there are 4 aces in the deck and 52 cards in total. But now the probability that you draw an ace on your second draw, well, if you picked an ace on the first draw, then that's going to be 3 out of 51, which is not the same as 4 out of 52. If you didn't pick an ace on the first draw, then it's going to be 4 out of 51, which again is not the same thing as 4 out of 52. So in either case, if you're doing this without replacement, then the trials are not independent, right? The probability of drawing an ace on your second draw depends on what happened on your first draw. So this is not binomial, okay, not binomial. Part C says a fair die is rolled 50 times and the number that is rolled, 1, 2, 3, 4, 5, or 6, is recorded. Okay, so again, this one is not binomial. Go ahead and give the video a pause. See if you can figure out why it's not binomial. Okay. The condition that is not satisfied in part C is condition 3. Okay. Condition 3 is that for each trial there have to be 2 mutually exclusive outcomes, success or failure. And here we don't have a clearly labeled success or failure. They're just recording what number was rolled. They're not saying that like rolling a 4 is success. They're just saying that they're just recording the number that's rolled. So this is not binomial, right? Condition 3. Because of condition 3. Okay, that's that one. Part D. In a class of 30 students, 55% are female. The instructor randomly selects one student, records the sex of the individual, asks the individual to sit back down, and randomly selects again from all 30 students. This experiment is repeated 4 times, and the number of females selected is recorded. Okay. So this one is binomial for sure. Okay. Success in this case is selecting a female student. The number of trials, well, it says the experiment is repeated 4 times, so n equals 4. Probability of success. Now, if you're thinking 50%, you're not reading the problem carefully enough, right? It's true that about half of the population is female and half of the population is male, but in this particular class, there are more girls than boys, right? 55% of the class is female. So the probability that you randomly select a female student is 55%, right? Which means the probability of failure, 45%. And then x, right? So x is the number of times that you are successful. That would be 0. You could be successful 0 times or once, or you could be successful all 4 times, right? So any of those are options for x. But yeah, this is definitely a binomial. You can go through the list and verify, right? It's like the experiment is performed a fixed number of times, right? 4 times in this case. The trials are independent, right? Because you ask the student to sit back down and then you randomly select from all 30 students again. So the trials are definitely independent. There are 2 mutually exclusive outcomes. You're either a female or you're not a female, right? And then the probability of success is the same for each trial of the experiment. So, so that one for sure was binomial. Now, the reason that binomial probabilities come up so frequently is because we can almost always turn an experiment into a binomial experiment. So even if it's not binomial per se, we can adjust it so that it is binomial. Just to give you an example of this, we determined that example 1C was not binomial. How might we adjust that experiment to make it binomial? So let's remind ourselves, 1C was this problem right here. We determined it was not binomial. So this one was the one where a fair die is rolled 50 times and the number that is rolled is recorded. So we can make this one binomial by choosing some outcome to be a success. So maybe you could say something like, well, if you roll an odd number, then that's success. And then instead of recording the number that's rolled, you just record the number of times that you roll an odd number, right? And then you let x be the number of times that you roll an odd number. And then x would be binomial, okay? It doesn't have to be odd, right? You could define any kind of success you want. So you could say rolling a 4 is success, right? So if you say let x be the number of times that 4 is rolled, then suddenly this becomes a binomial variable because either you roll a 4 or you don't roll a 4, right? But the way that it's written is not binomial. If you're just recording the number that's rolled, that's not binomial. But if you define some kind of success, then it is a binomial experiment. We weren't asked to do this, but looking at part B, you could make part B binomial pretty easily as well. All you have to do is put the cards back in the deck before you make the next draw, right? So, so yeah, you can almost always turn probability experiment into a binomial experiment, and that's why they're so important to understand, and that's why they come up so much. But how might we adjust this experiment to make it binomial? Define some outcome to be success. For example, let x be the number of times you roll a 4. something like that. Okay, so we've spent a good deal of time trying to determine how to determine if something is a binomial variable. Once you have that, once you know that something is a binomial experiment, how do we compute probabilities involving that experiment? That's what we want to be able to do. So for example, let's say that x is the number of times we flip heads in 20 flips of a coin. Clearly, x is a binomial variable, right? You have success and failure. You're flipping a fixed number of times. Each trial is independent of the last one, right? So this is a binomial variable for sure. Now, little p is the probability of success in each trial. So in this case, little p is 0.5, right? You have a 50% chance of flipping heads, okay? So p is 0.5. But something like p of 7, this symbol is meant to represent the probability that x equals 7. In other words, it's the probability that out of the 20 trials, we flip heads exactly 7 times. How do we compute that? How do we compute the probability that x equals 7? If you're thinking, well, the answer should be just 7 out of 20, then you're way underthinking this. Okay? It's not 7 out of 20. Think about it. It's like, if that's your logic, then you would say the probability that you flip heads 20 times would be 20 out of 20, or in other words, 1. In other words, you have a 100% chance of flipping heads 20 times. Obviously not true, right? That's obviously not true. So you can't just take the number, you can't just take x and divide it by the number of trials, right? You can't say it's 7 out of 20. No, not even close, right? The probability we flip exactly 7 heads, that's tricky. It's complicated, right? For now, we're going to use StatCrunch to do it. But later on in the lecture, I'm going to tell you how StatCrunch is computing these values. So we'll talk in more detail about what StatCrunch is doing behind the scenes. For now, let me just show you how to use StatCrunch to compute this probability, okay? So in StatCrunch, we're going to go to Stat, and then Calculators, and then Binomial. And once you do that, you'll be prompted to enter something for the number of trials, and then something for the probability of success. And then you'll also have to enter in the inequality that you want to compute. So let me give you a few examples. This one says, according to Experian Automotive, 35% of all car-owning households have a red car. Okay. Part A says, in a random sample of 20 car-owning households, what is the probability that exactly 5 have a red car? Okay. So first of all, this is a binomial experiment for sure. We have success and failure. Success in this case is owning a red car. Failure would be not owning a red car, right? And 35% of households have a red car. So the probability of success is 35%, right? Little p is 0.35. We're performing the experiment a fixed number of times, right? We're going to go and look at 20 car-owning households, so n equals 20 in this case. Each trial is independent of the last, right? Like, you owning a red car has nothing to do with whether or not somebody halfway across the country also owns a red car, right? So yeah, this is a binomial experiment for sure. So we're going to go to Stat, Calculators, Binomial. And then when we get there, and actually this is how I would want you to show your work on this kind of problem. I would want you to write that down. I would want you to tell me where you go in StatCrunch to get your answer. Because if you get the wrong answer, I can still give you partial credit if you went to all the right places, okay? So write down Stat, Calculator, Binomial. When you get there, you're going to be prompted for the number of trials, which in this case we said was 20, and for the probability of success, which in this case we said was 0.35. Now, the probability we're looking for is that exactly 5 own a red car. So we're looking for the probability that x equals 5. So we want to know, what's the probability that out of the 20 people that we survey, exactly 5 of them will be quote unquote successful, right? Let's go to StatCrunch and see what we get. So we go Stat, Calculators, Binomial. N is 20. P is 0.35. We're looking for the probability x equals 5. So you want to change this inequality here to an equal sign. And then you'll notice that it gives us a nice little probability histogram, well, actually a bar chart, I guess. But and then it highlights in red the outcome that you're interested in. So in this case, we were looking for the probability x equals 5, and so it highlights that bar. And there's that probability, so 0.1272 approximately. Okay. 0.1272. Yeah, that's right. Okay, so that's that one. Part B says, in a random sample of 20 car-owning households, what is the probability that less than 4 have a red car? So we're going to do the same thing, right? Stat calculator's binomial, n equals 20, p equals 0.35. But this time, we're looking for the probability that x is less than 4. Okay? So let's go to StatCrunch and see what that is. So I can just come back here to my calculator. Right, I got there by going stat calculator's binomial, and then it pulls up this thing, right? Okay, but you put in 20 for n, 0.35 for p, and then we're looking for the probability x is less than 4. So I need to change this inequality to a less than sign, and then I need to change this number to a 4. And again, you'll notice they highlight all of the bars in red that you're interested in. You're looking for the probability x was less than 4, so they're coloring in 3, 2, 1, and 0. Okay. Anyway, there's that probability. So about 0.0444. Okay, part C. In a random sample of 20 car-owning households, what's the probability that at least 2 have a red car? Okay, so again, you're going to go to the same place, punch in the same things, but this time we want the probability that at least 2 have a red car. At least 2 would mean that 2 of them have a red car or more. So 2 or more. So we want x to be greater than or equal to 2, right? 2 or more. Let's see what we get. So we want to change this to a greater than or equal to 2. That's almost certain to happen, right? It's 0.9979. So like a 99 point, almost like a 99.8% chance of happening. It's almost certain, 0.9979. Okay. So this is how we compute binomial probabilities. Let me give you another example. This one says 2 out of every 100 people who take Depakote to relieve their migraine headaches experience weight gain as a side effect. A random sample of 30 users is obtained. Find the probability that the number who experienced weight gain as a side effect is between 1 and 4 inclusive. Okay, so first of all, this is a binomial experiment, right? You either experience weight gain as a side effect or you don't. Okay, so it's a binomial thing for sure. Whether or not, and it's also independent, right? Like whether or not you experience weight gain has nothing to do with whether or not somebody else did. So yeah, this is totally, they're independent trials. You're running the trial a fixed number of times, et cetera, et cetera. So since it's a binomial problem, we're going to go stat calculators binomial. When you get there, you're going to need to be able to enter something for n, number of trials. Number of trials in this case should be 30, right? It says a random sample of 30 users is obtained, so n equals 30. And then you'll have to enter something for the probability of success, p, right? So p, probability of success. Well, in this case, we're considering weight gain to be success, right? Now, what does the problem say about how many people experience weight gain as a side effect? Well, they say 2 out of every 100 people who take Depakote experience weight gain as a side effect. So the probability of success is 2 out of 100. Or if you like it as a decimal, then you can put 0.02. Okay. So we're going to go to the binomial calculator and put in these parameters. And then we want to compute the probability that that x is between 1 and 4 inclusive. What does that mean? Well, we're looking for the probability that x is between 1 and 4. So I'm going to write it like this, just exactly the way it seems like it should be, right? X is between 1 and 4. When it says inclusive, it means that x could be 1 or 4. So in other words, if it said between 1 and 4 exclusive, then you would just write this. Right? You would look for the probability that x is strictly greater than 4, or strictly greater than 1, but strictly less than 4. That's if it said exclusive. When it says between 1 and 4 inclusive, that means that x is also allowed to be either 1 or 4. So that's what that would look like. Okay, let's go to StatCrunch to see how we can do this. So you'll notice that, like, in order to type in what we wrote down on our paper a second ago, we need an extra space, an extra box to fill in another number, and there isn't a way for us to do this now. Now you could figure this out by like piecing things together, like putting in probability x equals 1, and then putting in probability x equals 2, and then 3, and then 4, and then adding those up, right? So that's one way that you could do it. There are other ways you could do it as well. But if you look up here, there's this button that says between, and if you click on that, then it gives you the extra space that you needed in order to be able to put numbers in here, right? So if I want to know the probability x is between 1 and 4, now I have a space to put both of those numbers. And I can say, well, the probability x is between 1 and 4, 0.1180. Oh, wait. No, I'm messing this up because I needed to change these parameters around, right? Let me do this from the beginning. We go to Stat, Calculators, Binomial. We're going to have 30 trials, we said. And the probability of success, we said 0.02. Okay, now I'll put it on between mode and put in 1 and 4. There we go. Okay, so there's the probability, 0.4542. Okay, so that's that one. So this is how binomial probabilities work. This is how we're going to compute these things. We're just going to use StatCrunch and let StatCrunch do the heavy lifting. One more thing to mention, and then I do want to show you what StatCrunch is doing behind the scenes here, right? So I want to show you like where it's coming up with these numbers, okay? So I promise you we'll get there. If you're one of those people that's like, but I have to understand why it works, you know, then believe me, I'll show you. Hang in there. But let me show you something else real quick. Okay, so you may recall from the previous section, section 6.1, that the expected value for x is the sum of all of the x times p of x's, and the standard deviation for a random variable x is actually, it's the square root of the expected value of x squared minus the mean squared. If we happen to know that x is binomial, though, we have some more information. So if we know that x is binomial, then it turns out p of x is, we can come up with a formula for it. And I'm going to show you where we get this formula here in a second, okay? But for now, just take my word for it, right? Like here's the formula that we would come up for this binomial variable. And so we can replace the p of x with this formula to obtain this result for the expected value. Now you may look at that and say, but that looks way worse than this. It does at first glance, but you can simplify this. You can do some gnarly calculations and simplify this to get something really nice. The expected value for a binomial variable x is just n times p. If you're interested in the details, here's a video that will prove it to you. So you can go ahead and click on that link to watch the video if you want. But anyway, for the rest of you who maybe don't care quite as much, let me just say that this should make some intuitive sense as well, okay? Because if you have n trials and each trial has probability p of ending in success, then you would expect n times p successes, right? In other words, like if you know that 35% of people own a car, own a red car, and you go out and you sample 100 people, then you would expect for 100 times 0.35, in other words, 35, you would expect 35 of them to own a red car, right? It just makes sense, makes intuitive sense. We also have a shortcut formula for the standard deviation. Here's the shortcut formula for the standard deviation, okay? So it's just the square root of n times p times q, which is really, really nice. So I want to give you an example of computing the mean and the standard deviation in StatCrunch, or not in StatCrunch, I'm sorry. I want to give you an example of computing the mean and standard deviation of a binomial random variable. And we'll answer some questions about whether or not these observations are considered unusual and stuff. So just as a reminder, generally speaking, an observation that's more than 2 standard deviations from the mean is considered unusual. So that's the criterion that we're going to use to determine if something is unusual. So number 5 here says, according to Experian Automotive, 35% of all households have a red car. In a simple random sample of 400 households, determine the mean and standard deviation of the number of households with a red car. Would it be unusual if in this sample of 400 households, 150 had a red car? What if 250 had a red car? Okay, let's answer the first thing first. So we have a random sample of 400 households. Let's determine the mean and the standard deviation. So the mean is n times p. That's going to be 400 times 0.35. Okay, let's see what we get. 140. So the mean is 140. Okay, standard deviation. All right, sigma is the square root of n times p times q. That's the square root of 400 times 0.35 times, well, if p is 0.35, then q should be 0.65. Right? Remember that q is the probability of failure. So q, right? So q is 1 minus p. So if we're saying that p is 0.35, 1 minus 0.35 is 0.65, and that's how we get q. Okay? Let's see what we get now when we punch this into our calculator. Square root of 400 times 0.35 times 0.65 is about 9.5. Yeah, I'll just round it to 1 decimal place. Say it's about 9.5. Okay, so there's the mean and the standard deviation. Now let's answer these questions. It says, would it be unusual if in the sample of 400 households, 150 had a red car? Well, my gut tells me no, because the expected value of households, or the expected number of households to have a red car is 140. So 150 doesn't seem that off, right? It seems like, yeah, that probably wouldn't be very unusual. But to verify that, we could say, well, how far above the mean is this? Okay, as long as it's less than 2 standard deviations from the mean, it's not considered unusual. So you could do that a couple ways. One way to do it would be to compute the z-score for 150, and if the z-score is less than 2, then it's not an unusual observation. The other thing you can do, and I think the way I'm going to do it, because I think it's going to be easier, is to just figure out what value is 2 standard deviations above the mean, because that'll serve as like a cutoff point for determining what's strange and what isn't. So if you're 2 standard deviations above the mean, that would be mu plus 2 sigma. Well, mu is 140 and sigma is 9.5. So what would that be? 2 times 9.5 is 19, so 159, I think. So 159 is 2 standard deviations above the mean. So as long as your value is less than 159, it's not unusual, right? And 150, right, is less than 159, so it's not unusual. 250, on the other hand, is way more than 159, so that definitely is unusual, right? So 150 is not unusual, but 250 is. Okay, and that's that. Okay, so these shortcut formulas are really nice. I mean, it's so quick to do this by hand when you know that x is binomial. But that's the catch, right? Is that x has to be binomial in order for this to work, in order for you to be able to use these shortcuts. So to sort of drive that point home, let's look at a couple examples, right? So this says, so note that binomial variables are a specific kind of discrete variable. The formulas derived in this section only apply to binomial variables. So here's an example. It says, let's say that in a particular sporting event, 2 teams play a series of games, and the first team to win 3 games wins the series. This is actually a pretty common scenario, except it's usually 4 games, right? Like if you're looking at the World Series in baseball, or like in the NBA or whatever, right? Like these are all first to win 4, right? First team to win 4 games wins the series. But in my case, I wanted to make it a little bit easier, simplify things a little bit. So I'm just going to say the first team to win 3 games wins the series. So if you think about it, that means that a series could involve 3 games or 4 games or 5 games, right? Because if one of the team wins the first 3 games, then they win the series, and the series is over after 3 games. But if, on the other hand, the first team wins a game, and then the second team wins a game, and then the first team wins a game, and so forth, then it could take up to 5 games before a winner is determined, right? Okay. Now let's say that this particular series has only happened 5 times in history, and that with the following results. So one series required 3 games, 3 of the series required 4 games, and 1 of the series required 5 games in order to determine a winner. So now part A says, let x be the number of games played in a series. That should say played. So let x be the number of games. I don't know what polyid means. Let x be the number of games played in a series. Is x binomial? And the answer is no. Hopefully you recognize that x is not binomial. It's not binomial because you don't have success and failure. It's not like they said, we counted up the number of times that 4 games were played. No, it said we just kept track of the number of games that were played in each series, right? So it's not a binomial variable. There are 3 possible outcomes for each trial. So no, it's not binomial. Now it says, construct a probability model for x. So even though it's not binomial, go ahead and construct a probability model anyway. Okay? We can do this. This isn't too terrible, right? So x is the number of games needed. It's the number of games played in the series. So x could be 3, x could be 4, or x could be 5, right? Now p of x, probability that x is 3. Well, one series required 3 games. One series out of the 5 series that have been played so far in history. One of them needed 3 games. So the probability you need 3 games in a series, 1 out of 5. Probability you need 4 games in the series, it says 3 of the series needed 4 games. So that would be 3 out of 5. Okay. And then probability you need 5 games in the series, it says 1 series required 5 games. So that would be 1 out of 5. And if you add that up, you get 5 out of 5, so everything makes sense. Right, it's looking good. So we've got, that's it. That's our probability model. And then finally, it says compute mu sub x and sigma sub x. So let's do that. So mu sub x, remember that's the same as the expected value. So that's going to be x times p of x plus x times p of x plus x times p of x. And then we're done. So we just need to work out the arithmetic here. So this is 3/5 plus 12/5 plus 5/5. That comes out to 3, so 12, 13, 14, 15, 20. That comes out to 20/5, or in other words, 4. Okay, so there's the mean. The standard deviation is the square root of the expected value of x squared minus the mean squared. Well, the expected value of x squared, let's do some scratch work, right? So expected value of x squared so we're going to do the same thing we did before, but we're just going to square the x's, right? So I'm going to get 9 times 1/5 plus 16 times 3/5 plus 25 times 1/5. Let's see what we get. I'm just going to go ahead and punch this into my calculator. So I've got 9/5 plus 16 times 3 is 48. 48/5 plus 25/5. That's 82/5. That's 16.4. So now the standard deviation, right? So the standard deviation is going to be the square root of 16.4 minus 4 squared. Oh, that's 16.4 minus 16, which is the square root of 0.4, which I think is 0.2. How nice is that? Oh, is that right? No, that's not right. Square root of 0.4. No, it's not. I should have known better. No, square root of 0.4 is 0.63. Well, we'll just leave it there, 0.63. But there's the standard deviation. Okay, so this is how we did stuff when we didn't. If the variable is not binomial, this is how you have to do stuff. This is how you have to find the mean and the standard deviation. Okay. This is using techniques from the previous section, right? 6.1. Okay. Now part B says, now let x be the number of times out of the next 4 series that 4 games will be played. Is x binomial? Construct a probability model for x. Okay. So this time we do have a binomial variable on our hands, right? We're being asked out of the next 4 series, what's the number of times that 4 games will be played? So we've got a clearly labeled success here, right? If a series requires 4 games, then that's considered to be success, okay? So yes, this one is binomial. This is binomial. And now remember, x is the number of times that 4 games are needed. It's possible that x could be 0, right? Because maybe each game in the next 4 series only requires 3 games, or it requires 5 games. Maybe none of them will require 4 games. So it's possible that x could be 0. It's possible that x could be 1, 2, 3. It's possible x could be 4, right? It's possible that all 4 of the next series require 4 games to be played, right? That is possible. So x could be anything between 0 and 4. Now, if we want to compute the probability that x is 0 or 1 or 2 or 3 or 4, then since this is a binomial variable, we can use the binomial calculator in StatCrunch to calculate these values. So we're going to go to Stat, Calculator, Binomial. We're going to put in for the probability of success. Well, let's see. We know that the probability that a series will require 4 games is 3/5, right? So that's the probability of success, right? The probability of success is 3/5. Number of trials is 4, right? Because this is in the next 4 series. Okay, so we're going to go to the binomial calculator, put in these things for the parameters, and then we'll be able to compute these probabilities. So let's do it. So it's Stat, Calculators, Binomial. I'm going to put in 4 for n. And I'm going to put in 3/5 for p. 3/5 is the same as 0.6. I'm going to put in 0.6 for p. And then I want the probability that x equals 0. That's 0.0256. So I'm going to write that down on my paper, 0.0256. Then I want the probability x is 1. I'm going to put in that on my paper. So for probability x is 1, 0.1536. Probability x is 2, 0.3456. Probability x is 3, 0.3456 again. Probability x is 4, 0.1296. Okay, so there's my probability model, right? That's how I would get my probability model. Okay, now it says compute mu sub x and sigma sub x, right? So compute the mean and the standard deviation. Now, because x is binomial, this is super easy, right? The mean is just n times p. That's going to be 4 times 3/5. Which is 2.4. Okay, and the standard deviation is the square root of n times p times q. That's going to be square root of 4 times 3/5 times 2/5, right? Again, P is probability of success, Q is probability of failure, Q is just 1 minus P. So if you have a 3 out of 5 chance of success, that means you have a 2 out of 5 chance of failure. So let's see. We're going to have square root of 4 times 3/5 times 2/5. And that comes out to about 0.98. Okay, and that's it. That's all there is to it. You could do this the long way, right? So you could use these formulas for the mean and the standard deviation to arrive at the same answers here. I just wouldn't recommend it. I mean, if you have a shortcut, you might as well take it, right? So whenever you can use the shortcuts, I would use them. But you could, right? You could use the longer formulas, and you should get the same answer, right? In other words, if I were to say 0 times this, plus 1 times that, plus 2 times that, plus 3 times that, plus 4 times that, and then add them up, I would get 2.4 still, right? I should still get 2.4. I'll leave that as an exercise to you if you're interested. Actually, you have some homework problems that I think ask you to do that so that you can see the connection between those topics. But yeah, so you can always use these formulas regardless. These formulas, though, you can only use them if you know that the variable is binomial. Okay, that's the moral of the story. So that's pretty much it. Like at this point, you can definitely tackle all of the homework problems. However, I'm going to continue to talk because I did want to talk about what StatCrunch is doing behind the scenes when it's computing binomial probabilities for us. So if you don't particularly care to know, then you're probably safe to stop watching the video at this point. But if you're interested in knowing what StatCrunch is doing behind the scenes, you know, how we come up with this formula and all of that stuff, then stay tuned for a second and we'll walk through the logic of it together, okay? It ties together a lot of the stuff that we did in chapter 5, which is really pretty nice. So here's what I'm claiming. I'm claiming that the probability of obtaining X successes in N trials of a binomial experiment is given by this formula right here, where little p is the probability of success and little q is the probability of failure, right? Little q is 1 minus p, of course. To convince you of this fact, I want to take you through an example. So this one says, according to the American Red Cross, 7% of people in the United States have blood type O negative. A simple random sample of size 4 is obtained, and the number of people X with blood type O negative is recorded. Construct a probability distribution for the random variable X. Okay. So they're going to select 4 people, and we're interested in recording the number of times a person with blood type O negative is recorded. Well, what's the probability that that happens? Right, it's 7%, right? Because 7% of people have blood type O negative. So, so let me just write that down, right? We know that the number of trials is 4, and that the probability of success is 0.07. So, if we want to construct our probability model, it's going to list off the possible values for X together with the probability that X takes on that value. What are the possible values of X? Well, it's possible that out of the 4 people that are surveyed, none of them have blood type O negative. It's also possible that exactly 1 of them has blood type O negative, or 2, or 3, or 4, right? So these are the possibilities. X could be 0, 1, 2, 3, or 4. Now I'm going to do a lot of scratch work to fill in this chart, okay? Let's look at the probability that X equals 0. If X equals 0, then this would mean that you would have to get 4 people that do not have blood type O negative. You would have to have 4 failures. Failure, 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 failure. Okay? Well, that's pretty easy. We know that the trials in a binomial experiment are independent, and because they're independent, probability of failure and failure and failure and failure, all of those ands are just going to turn into multiplication. So this is just probability of failure times probability of failure times probability of failure times probability of failure. And the probability of failure we said was Q, right? The symbol that we're using for that is Q. So I'm going to call this Q to the 4th power. And I'm going to leave myself some space here because I'm going to want to come back in and fill in some stuff in front of it. But for now, yeah, I'm going to say Q to the 4th power. Right? That's the probability of failure. Now I can get an actual number for that if I'm interested, right? I know that if the probability of success is 0.007, then the probability of failure is it's 1 minus 0.07, which is 0.93, right? And then 0.93 to the 4th power is 0.7481 approximately. So 0.7481 is that answer there. Okay, now let's look at the probability X equals 1. So probability X equals 1. This means that we have exactly 1 success. We choose somebody, exactly 1 person with blood type O negative out of the 4. That means the other 3 have to be failures, right? So this could happen if we get a success and then 3 failures. Or it could happen if we get a failure and then a success and then 2 more failures. Or It could happen if we get 2 failures, a success and a failure, or it could happen if we get 3 failures and then a success. So there are 4 ways that that can happen. Now, we know that in a binomial experiment, each outcome is mutually exclusive, and so all of these ORs are going to turn into pluses. We also know that since the trials are independent, this is all just going to turn into multiplication. And since multiplication is commutative, that is, since we can do multiplication in any order we want, what we really have is 4 copies of exactly the same thing, okay? So instead of writing it out 4 times, I'm just going to, well, maybe I'll say it like this, right? So maybe what I'll say is, what I'm going to have is the probability of success times the probability of failure multiplied by itself 3 times. And this is going to happen 4 times in total, right? 1, 2, 3, 4. And I'm going to change all of those ORs to additions. Okay, so really this is 4 times p to the first power times q to the third power. Okay. In case we're curious to know what that is, let's see. 4 times p, 0.07, times q, 0.93 to the third power. Whoops, 0.93 to the third power is 0.225. Maybe I'll go 5 decimal, 0.22522. Which means this one I should have maybe gone out 1 more decimal place. Okay, but that's that. Okay, sorry about that. It cut out there for a second. Anyway, but yeah, so 6 ways that this can happen. So let's see. But again, we notice that they're all just copies of the same thing. Really what this is going to boil down to is it's 6 times 2 successes times 2 failures, right? So 6 times p squared times q squared. And if you're interested in what the number is, right, 6 times p squared times q squared is 0.0254. 543, I guess, if we're rounding to 5 decimal places. So there's that one. Now, what you might notice with these exponents is if you look at q, as we move up, it went 2, 3, 4. So it's increasing as we go up. P, on the other hand, is decreasing. It goes 2, 1, and 0, p to the 0 power, right? Because anything to the 0 power is just 1. So adding a p to the 0 power here doesn't change our answer. And then if you look at the numbers, well, there's not a clear pattern there. Like here, we can definitely say it's 1 because again, 1 times anything is just the same thing. But notice that this number is the number of ways that we can get this, right? So there was only 1 way to get 4 failures, but there were 4 ways to get 1 success and 3 failures, 1, 2, 3, 4, and there were 6 ways to get 2 successes and 2 failures, 1, 2, 3, 4, 5, 6. So for the next one, for probability x equals 3, I'm going to see if I can just guess at what it should be. So the first thing I need to do is I need to figure out how many ways I could get 3 successes. Well, I think there are 4 of those, right? There are 4 ways that I can get 3 successes. It happens if I do SSSF, what did I say? SSSF SSFS, SFSS, or FSSS. So 4 ways, right? 4 ways that can happen. 4 ways that can happen. So it's going to be 4 times p to the what? Well, if I use my pattern, 0, 1, 2, it should be p cubed. And then q to the what? Well, if I use my pattern, 4, 3, 2, should be q to the first. Now, if you think about how these numbers relate to this number right here, notice that this exponent matches that exponent. 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 So it looks like we're just raising p to the number of successes. What about q? Well, q is sort of the opposite, right? Remember that we had n trials. So here we're doing n minus 0. Here we're doing n minus 1. Here we're doing n minus 2. And here we're doing n minus 3. So it's always n minus x. So here we have x, and here we have n minus x. Okay? And now, as for this coefficient, we went 1, 4, 6, 4. So it's kind of a strange pattern, but what I'll point out to you is that 4 is the number of ways that we can choose one success out of 4. In other words, this is 4 choose 1. Okay? And 6 is the number of ways that we can choose 2 successes out of 4 trials, right? So this is 4 choose 2. And this 4 is the number of ways we can choose 3 successes out of 4 trials, right? This is 4 choose 3. It just so happens to be the same thing as 4 choose 1. Okay? So anyway, we should see what number that is. That's 4 times 0.07 cubed times 0.93 to the first. That's 0.00128. Okay, but the moral of the story now, probability x equals 4. Okay, so we need to choose, there's only going to be one way this can happen, but to show you where the formula comes from, we would say, well, this is 4 choose 4. We need 4 successes. So out of our 4 trials, we're going to choose 4 successes, right? 4 choose 4 times p to the number of successes times q to the number of trials minus the number of successes. So if you simplify that, 4 choose 4 is 1, p to the 4th, q to the 0. And just for the curious out there, we would say it's the probability of success to the 4th power is 0.00002. That's why I wanted to round to 5 decimal places, because if we didn't, then this last one would just be 0. But there you go, right? Those are the probabilities, and what you notice is that this formula holds, right? When you're trying to determine the probability of obtaining x successes, you need to do the number of trials choose number of successes times the probability of success raised to the number of successes times the probability of failure raised to the number of failures, right? Which is going to be the number of trials minus the number of successes. So that's that idea. That's where that formula comes from. And this is the formula that StatCrunch is using when it computes probabilities for us. Here's an example, just doing one by hand, right? So remember our formula, p of x is n choose x times p to the x times q to the n minus x. And let's use this to calculate. It says we toss a fair coin 20 times. Find the probability of obtaining exactly 7 heads, right? Well, this is going to be, we have 20 trials, right? So it's going to be 20 choose 7 times p to the 7th. Well, p, if we're tossing a fair coin, the probability we flip heads is 50%, right? So it's times p to the 7th times q. Well, if we have a 50% chance of flipping heads, then we have a 50% chance of flipping tails, right? So times q to the 20 minus 7. To do 20 choose 7, you just have to use your favorite combination calculator. 20 choose 7 is 77,000. It's 77,520. Okay, times 0.5 to the 7th times 0.5 to the 13th. I'm just going to throw this all into my calculator at the same time. But let's see what we get. 77,520 times 0.5 to the 7th times 0.5 to the 13th equals, or it's approximately equal to 0.0739. Okay, and that's that. Okay, I'm not gonna go over this second example, I think, because you get the idea. But what I will do is show you that hopefully you get the same number when you do this in StatCrunch. So if we go to StatCrunch real quick, we would go to Stat Calculators, Binomial, and then we would put in this case, 20 is our sample size, and our probability of success is 0.5, and we want the probability that x equals 7. And sure enough, 0.0739. Okay, so there you go. So that's what StatCrunch is doing behind the scenes. You may wonder, well, what about for these kinds of probabilities that we looked at before? Well, for these things, what StatCrunch is doing is it's computing probability x is 8, and then probability x is 9, and then probability 10, 11, 12, 13, and then it adds all of those up. Okay. I'm not going to take you through an example of working all that stuff out because it would take us forever. But that's why we use StatCrunch, right? Because these calculations are tedious, and so we let StatCrunch do the heavy lifting. But I just wanted to give you the reasoning behind what StatCrunch is doing, so that you don't accuse me of just doing some magic or making you just believe, take my word for it. Like, no, these things, there's actual mathematics involved. It's just going on behind the scenes because it's kind of tedious math, and so we'd rather let StatCrunch do it for us. But there's your homework assignment, and we'll see you in the next section.